Well, wow. Well, thanks everybody for piling in here. It's going to be 40 minutes, so keep your legs strong, and we'll go ahead and get started. So what I'm going to be doing in this talk is covering three things. These are three very complex things, oftentimes requiring a little bit of like mind explosion recursion. So we're going to try to do our best to work our way through it. So let's just get right into it. So for those of you who might not be familiar, I'm Brandon Phillips. I'm the CTO and co-founder of CoreOS. CoreOS is a company that's developed a lot of fundamental open source projects for this whole ecosystem. NetCD is a project we introduced in 2013. I'll be talking a little bit about primary data store of Kubernetes, CoreOS Linux, Rocket, and we're big contributors to Kubernetes as well. And then we have enterprise products, Tectonic, which has upstream pure open source Kubernetes at its core and builds a bunch of features around that are necessary for enterprises. And Quay, which is our container build system and registry hosted at quay.io or behind the firewall with Quay Enterprise. All right, so let's get right into it with scaling. This is going to be the first topic. I'm essentially going to cover from the bottom essentially all the work that's happened over the last release or so, from the very bottom all the way to the very top of Kubernetes. So let's start with NetCD, since it'll play into the story overall in several different places. So NetCD is the primary data store of Kubernetes. It was introduced in 2013. If you think of like the primary data store of something like WordPress or something, Kubernetes is to NetCD as MySQL is to WordPress. So we use everything that Kubernetes does every time you write into the API. NetCD is persisting to disk and replicating. It is a replicated consistent key value store. There's a lot in that, in those few words there. But essentially what it means is that those keys that Kubernetes wants to be persisted get replicated in a manner across multiple machines so that we're resilient to individual machine failure. It allows for revisions and event streams so that as the keys change, we're able to go back in time, do things like consistent views of the data 5 minutes ago, 10 minutes ago, and this is an important primitive for Kubernetes, and some of the fundamental UX and design interactions in Kubernetes build upon this. And then finally, the reason that we replicate and the reason that the system is consistent is because we want to achieve auto leader election for availability. So Kubernetes, the whole design goal here is that we're able to have systems that kind of are self-healing, that are able to take care of themselves. Operators can focus on their application. And so we need a database that is able to kind of take care of itself as well. And so what NetCD does in the face of failure, it detects failure, auto leader elects, and allows you to continue sleeping while the computers figure out how to continue working. So for a quick demo of just NetCD, just so everyone's on the same page of what it is and why it's built, we're going to start with this service that is at play.netcd.io. This is a system for people to get used to Kubernetes, or get used to NetCD and how it works. Now, this is sort of like an MMORPG for NetCD, so you'll see that as I'm in this talk, people are logging in up in the corner there, which means that generally what will happen is about 20 or 30 seconds, people will start clicking on the little circles there and clicking buttons for me, and I can talk through different failures. If that doesn't happen, it's OK. There we go. So what NetCD is doing here is that we have 5 members in this NetCD cluster, and we're able to write into the NetCD cluster, submit new entries into the NetCD cluster, and the NetCD cluster continues to work until people kill too many members. And so there's, in the symbolism here, we have red means that the NetCD member has failed, blue means the NetCD member is up, and green means that it's the leader. So I'd kindly ask all the trolls to back off for a second here. So I can have an operational cluster for just a moment. So what I'll do is I'll recover 3 of these NetCD members. They come back up, and now I have a working cluster. NetCD is able to work with a simple majority. It works like our democracy, which we will all see in action today. And so I'm able to submit new values into etcd. So if I set foo to bar, baz, or whatever, and I click submit, what will happen is that this will replicate to all of the different things, and the hash will update, et cetera. And you can see here that as I click and kill the machines, what will happen is that leaders automatically get elected. It's like that new HBO show, Survivor. All right, good? Good. So that's what etcd is. It stores keys and values. It replicates those between machines, and it automatically recovers from failure. Any questions there? All right. So etcd has been around since 2013. And in the last few months, we've introduced a new version of etcd called etcd v3. We did a little bit of a Firefox. We did etcd 0.4, etcd 2, and then etcd 3. Just skip 1.0. Nobody cares. So etcd v2 was designed to support a really simple use case. The simple use case was we have all these CoreOS Linux machines, and we want those CoreOS Linux machines to coordinate reboots. And so in that case, you maybe have on the order of thousands of machines in general, and those thousands of machines really only have one piece of metadata, which is, can I reboot right now? So you're looking on the order of just a few, maybe a megabyte at most, maybe a couple megabytes. And so with Kubernetes selecting etcd as its primary data store, we could only scale to about 1,000 nodes because we needed to hold on to about 200 megabytes of data in order to have those 1,000 nodes. We're way past the original design goals of etcd. And so with etcd v3, we redesigned a lot of the internals of etcd, taking and holding on to the exact same consensus systems, the underlying Raft library, but rebuilding the actual data store to be able to support 3,000, 4,000, 5,000 members inside of a Kubernetes cluster and beyond, while holding on to event history. And the event history gets important later. So we're able to very handily handle a gigabyte, 2 gigabytes, 3 gigabytes of keys inside of etcd, which is necessary to scale to this size. And testing is underway with live clusters of 5,000 nodes plus. And so etcd is clearly in a good spot. Other parts of Kubernetes are now the scaling limit. We've pretty much taken all the low-hanging fruit, and etcd is a data store that, as we'll see here in a moment, really shines in its little niche that is consistent, replicated key value stores. Okay, so let's take a look through history a little bit. So this was what etcd 2 compared to Consul and Zookeeper looked like about 8 months ago. So Zookeeper is about at the top here as far as performance, being able to handle requests per second. etcd was somewhere in the middle, and Consul was coming in third place. And it wasn't just about how many keys could you slam in, but it was about what does the performance look like when you're slamming lots of keys into the database. And so a very common problem with these sorts of databases like etcd is that you need to do this thing where you have all this data streaming in, and it's this write-ahead log. So every time a change comes in, you're appending to this log. And at some point, the log grows to the point where you need to truncate. It's called snapshotting, and it can cause performance degradation in the cluster. And so here's in this trace, we can see a snapshot is cause degradation. And in fact, later, a snapshot gets triggered and causes a leader election because the etcd member is no longer responding. And this is common inside of Zookeeper as well. Snapshot was triggered election here inside of a Zookeeper cluster. And so what we did was we focused on how to solve this problem really nicely with etcd v3. And what you get is this really tight tolerance band. And this becomes really important because you don't want to get paged with false alerts when the system's just acting normally. Oh, the system had to do a snapshot? Well, the system always has to do a snapshot. Don't page me because a leader election is happening. And so we have this really consistent band of latency performance now inside of etcd v3 because of the work that we did, where within 10, 20%, we're able to handle the same requests per second pretty handily. And this is at 2 million keys at 256 bytes per key. And once you kind of zoom out a little bit, it looks really good. We see these latency spikes. The blue line is Zookeeper, which is a very nice thing to compare against, pretty battle-hardened system. And we see etcd essentially rock steady across the latency spectrum. And then the other thing that we did was we wanted to reduce memory consumption, resident memory consumption. So etcd is being asked by Kubernetes to hold on to gigabytes and gigabytes of data. And in order to do that, we can't have this huge overhead. So before, if we were asked to hold on to 512 megabytes of data in NetCD v2, it would cost us about 10 gigabytes of resident memory. Zookeeper, holding on to about the same amount of data, asks for about 2.5 gigabytes of resident memory. And in NetCD, we only do about a 30% markup in order to do our work and all the marshalling and unmarshalling over the network and the snapshotting. And we hover around 0.8 for 512 megs of data. So we're very handily able to, at this point, have tight latency tolerances, be resilient to various leader elections triggered by snapshots, and take care of your memory efficiently. And then the other work that we've done is that we have sort of these chaos monkey systems that run these long-running Kubernetes clusters. We have this fun one that you can play around with from your phone and troll the speaker, but also we have long-running ones that essentially check all the performance metrics of NetCD. So in summary, we did a lot of work. The graphs look good, and Kubernetes is in good shape riding on top of NetCD v3. So the story with NetCD v3 and Kubernetes is that it is an option in Kubernetes 1.4. You can turn it on. If you run Kubernetes today on top of NetCD v2, you can deploy NetCD v3. Your cluster will remain the same. There are scripts inside of the Kubernetes repo that can help you migrate your v2 keys into v3 keys and take advantage of these new things. But if you're launching a new cluster, there's really no reason, if you're using 1.4, not to just turn on the NetCD v3 flag and start from NetCD v3 for all your new clusters. All right, so we've hit a pretty good scaling milestone with NetCD. Any questions on this? Good, OK. So another neat thing that we've done in the last few days is we've introduced this thing called NetCD Operator. The NetCD Operator is able to run Kubernetes or run NetCD on top of Kubernetes. So we're starting to get really meta and recursive right off the bat here. But the idea is that we're going to be moving to a world where we want Kubernetes moving Kubernetes, which will be the next set of our slides. And what the operator allows us to do is really simply use the Kubernetes APIs to manage NetCD itself. So I have a Minikube. I have a Minikube cluster running on my laptop. If you're not familiar with Minikube, it allows you to run Kubernetes really easy on your laptop. And so if I do kubectl get pods, what I'll see here is that I have the NetCD operator running and then an NetCD cluster. Looks like that's getting cut off. Is it getting cut off? OK. OK. And so this NetCD cluster actually is using this concept of an operator, which is a thing that operates applications for you. So if I do kubectl get NetCD clusters, what I'll see is that there's a NetCD cluster. So we've extended the Kubernetes API to be aware of NetCD clusters as an object. And what is in this NetCD cluster manifest is really just two things. It's what version of NetCD do I want running and the size of NetCD. And the operator is actively going to manage this cluster for me. So if I do kubectl get pods, and then I decide that I don't particularly like this pod right now, I'll delete the pod. And then what we'll see happen is that, well, too quickly. Oh, maybe not. So what will happen is that NetCD's operator will detect that the pod is terminated and then launch a new pod as a replacement and keep the NetCD cluster healthy and running. OK. So that's going to be an important thing as we start to discuss the idea of self-hosted Kubernetes in the next section.
So running this CD as pods on Kubernetes, when
correct.
That happens, is that part of GIFEE?
Sorry? So this is part of NetCD v3. So this utilizes a lot of the administrative APIs in NetCD v3. And we only launch NetCD v3 and above clusters in these pods. And so it took a second, but you see here that we now have an NetCD v3 or NetCD 3 pod that's 14 seconds old. So the NetCD cluster is under active management. And the operator can do other things like backup NetCD and do disaster recovery and that sort of stuff, as described here. There's a blog post on it. It's all open source. You can find it under github.com/CoreOS/NetCD Operator. It's a single deployment to put it on your cluster. OK, so the next topic is self-hosted Kubernetes. So if you're not familiar with the concept of self-hosted, it's a pretty common computer science idea. So in the case of a lot of programming language, they're self-hosted. So you write the compiler for the programming language in the programming language itself. Your C compiler is not written in assembly. So it's written in C. So in the case of GCC, they take the GCC source code, they run it through an old version of GCC, out pops a new version of GCC. Golang just became self-hosted as well, so majority of Go is written in Go. So you take the Go source code, you run it through an old version of Go, you get a new version of Go. It gets a little bit more noodly when you start to think about things like operating systems or Kubernetes. So let's use an example. This is young Linus Torvalds. Linus used an operating system called Minix and wrote this new operating system called Linux. Out pops Linux. Neat. I love personal email notifications. I don't know what tab is doing that. Hopefully nothing embarrassing happens. So the next thing that Linus did, Linus got a little bit older, more mature, and Linux was actually running. This actually just happened in a few months. I think it's funny to use like a 40-year-old Linus versus 21. And so Linus already had Linux, and so he took the Linux source code. Linux was able to run GCC, and then out pops a new version of Linux. So we need to apply the same concept to Kubernetes. So today we have all these tools that kind of deploy Kubernetes on our behalf and then set Kubernetes up. So they talk to AWS, they deploy AWS, they do some configuration management, and then Kubernetes API endpoint pops out at the end. But what we want to do with self-hosted Kubernetes is we want to move to this world where instead of these tools essentially taking care of this whole stack, the tool takes care of the infrastructure, let the infrastructure tools focus on infrastructure, and Kubernetes takes care of Kubernetes. And so the advantage with this sort of platform is that we can use, say, kubectl and actually upgrade Kubernetes. And it works the exact same way whether we're on AWS or we're on Azure or perhaps we're on bare metal. We can use the exact same APIs, the exact same process to upgrade Kubernetes on any type of infrastructure that you have. So the goals here with self-hosted is that we use the compute, networking, and storage abstractions that we love Kubernetes for. The reasons that we use Kubernetes in the first place is that it allows us to abstract these things. The infrastructure tools focus on infrastructure, and it provides a foundation by using those abstractions to automate the upgrade of our clusters and scaling. So the way this looks in practice is that we'll say kubectl minus n kube system get daemon sets. We'll see API server and proxy running as daemon sets. And we'll see controller manager and scheduler running as deployments. Now this has a lot of natural advantages because let's say that we want to scale our scheduler. We can just edit the deployment of the scheduler and scale it. So obviously, like the proof is in it actually working, not necessarily it looking good on architecture slides. So I've gone ahead and launched a self-hosted cluster. All of this is based on Bootkube, which is an incubator project introduced by CoreOS. But we've wrapped really nice user experiences on top. So this is the essentially installer for Tectonic, which is what I use. But underneath, it's just using the infrastructure of Bootkube. And out the other end, what I get is a fully working Kubernetes cluster that's self-hosted. So if we dive into the kube system, as described, we see that there's the kube scheduler in here. There's 2 pods running. We can, if we need to make an HA Kubernetes, it's really simple because we just talk to the Kubernetes APIs and we say, scale up the number of schedulers so that in case a couple machines go away, my application keeps working. And we can see that those pods get launched and they get put onto machines that are appropriate for running the Kubernetes scheduler. And similarly, you can come in and see the daemon sets running. And the nodes that are actually doing all of the management of the cluster simply have this label on them that say master equals true, which means it's appropriate for things like the scheduler and the API server to run on top of them. And so this is all using Kubernetes APIs. The great thing about this is if an API server goes down or I lose a scheduler, I actually can just debug it. I can look through the events here inside of Kubernetes and see, oh, that's why like a container that was running the scheduler just came up or it just went away, et cetera. So that's the big concept with self-hosted Kubernetes is that we are moving towards this whole model of Kubernetes managing Kubernetes. Yeah. That is a great question. So what about the first deployment of Kubernetes? How do we bootstrap our way into it? So this is what the Bootkube tool actually does. And if you want to learn how the boot kube works, I'll bury the lead a little bit. Essentially what happens is we launch a temporary Kubernetes as a single process. Inside that single process is your scheduler, API server, etcd, everything you need. And then we pivot onto the actual real Kubernetes. And then we do all sorts of tricks to ensure that in case of power outages or whatever, you don't need to bring that temporary Kubernetes back up. And so if you want to learn about Kubeception, Aaron Levy is giving a really deep dive on self-hosted. But if you want to just get the results, you can just go onto BootKube, follow the AWS and GCP guides, and try it out. The other thing is that there's a lot of deployment tools inside of the Kubernetes ecosystem today. There's kubeadmin, kops, et cetera. Our hope with all of this self-hosted stuff is to show that it is a compelling deployment model, show that it is stable and that people can actually run real workloads on top of it while these things are happening. And we're working closely with the kubeadmin team. We've written up a design doc on how kubeadmin can do self-hosted. We are working with everyone else in the Kubernetes community, including Sigma Cluster Lifecycle, on essentially making this, if not the default, at least one of the premier choices for operating Kubernetes inside of production environments. BootKube is really a tool that we've been working on that proves out the model, brings all the things together into a cohesive set. There's a lot of work that needs to happen inside of Kubernetes to make it a perfect system. Right now, it's a 99% system. Any questions on self-hosted? Cool. All right. So we'll move on to federation. This is a real whirlwind, like a lot of topics in 40 minutes. So with federation, the big idea is that today we have Kubernetes. This is what a single Kubernetes cluster looks like. API server holds onto the state of Kubernetes. It's designed for single domain failures. So you want to put a single Kubernetes cluster inside of, say, a single data center. You want to put a single Kubernetes cluster, say, inside of a couple of racks that are in a single power failure domain, et cetera. And the single cluster is going to handle thousands of machines. So that's what Kubernetes is designed for. Single Kubernetes cluster is designed to be tolerant to individual machine failures, not a truck hitting your data center. Make sense? OK. The idea with federation is that it's kind of like self-hosted, where we're using Kubernetes at the bottom. The idea with federation is that we're using and managing multiple Kubernetes clusters by putting Kubernetes on top. And so what federation looks like is that we have very similar. You have the kubectl command line tool. It's talking to this special API server. That's the federation API. It's persisting all of its data in a replicated etcd that's hopefully running across all of your various clusters that are being federated. There's a federation controller manager that's actually ensuring the workloads end up on the machine or inside of the clusters that you'd like them to end up into. And then every single cluster underneath is just a normal Kubernetes cluster that actually is sort of blissfully unaware that this federation thing is actually happening to it, because the federation controller manager is just another client scheduling replica sets or pods or services to the cluster. So it's a lot to digest. Can I get like a show of hands if that all made sense? Great, OK. So that's the big idea with federation. So the API server in that etcd holds state for multiple clusters, like what services and replica sets you want running across your clusters. It spans multiple failure domains. And so ideally, you will have a federation cluster that's running in New York, San Francisco, and maybe Tokyo, or maybe like 3 places that aren't always disaster movies. But it spans multiple failure domains and is resilient to, like, just like etcd, 1 of the 3 or 2 of the 5 failure domains going away. And it coordinates between clusters. It's not actually for managing the individual machines in a cluster. So if you think about federation as the kubelet is managing processes, the federation controller manager is managing clusters. So it's like federation's kubelet is another cluster, if you want to go by analogy. OK. So if you notice that all my diagrams are super slick up until now, these I forgot to update. So you're going to have to bear with me on this. So the API server talks to an API server on the cluster, or actually multiple API servers. And that API server then schedules work, say like an Nginx process, and then that's the replica set going through. Now with services, what happens is that the Federation API, it now has this replica set scheduled to the individual nodes, and then it creates a new service, say an Nginx service, that ends up getting load balanced. So what we're going to do is I have an actual live Federation cluster that I've set up last night. Hopefully it's still running, so let's go ahead and play around with that for a second. The cluster that I'm playing with is set up using, where is it? Kelsey. There it is. Kelsey Hightower has probably the best instructions on how to set up the Federation clusters today. It runs you through setting up a Federation cluster on GCP, along with all of the load balancing and DNS and everything that you need to make it happen. It takes about 10 or 15 minutes to go through the entire thing, but I've done it for you so we can play around with it. So the big things that happen here is that I have, similar to those diagrams, those really awesome diagrams that you all remember from just a second ago, I have Nginx deployed against my federated cluster. And so I have this, kubectl is talking to this Federation cluster, which is a subset of a real API server. So if I try to run like git pods, it's not going to say there's any pods available because API server, Federation API doesn't deal with machines, it deals with clusters. So it doesn't know about pods, it knows about replica sets and services. And so what we can see is git replica sets. And what we'll see in here is that there's replica sets for Nginx. I have one replica set that is replicating only over the US domains, and I have another replica set that's going over my other clusters. And so if I go and do git clusters, what I'll see is that I have 4 clusters in this Federation. Oh, shoot, sorry, this is getting cut off. Somebody tell me. I have 4 clusters in this Federation. So there's East, West, Central, Asia East, West, Europe West, US Central, US East clusters in here. And I have, we can go ahead and dive into this replica set of Nginx US. So YAML. And what we'll see inside of this service is that it has a bunch of annotations. This annotation says, I want this replica set to only be scheduled to US, my US clusters, and I want there to be some policy around how many replicas end up in which cluster, and I want you to rebalance those in case anything happens, et cetera. And so you're able to express really complex failure domain logic inside of the Federation API, and the Federation API takes this into account when it talks to the clusters. So if we dive down into one of the individual machines, so I'll go into the cluster in US East, which should have a couple of pods of Nginx running, hopefully, yay. So inside of here, we have this, these couple of pods based on the policy running inside of US East. And if we go ahead and check out the load balancer that the Federation API is set up by looking at services. If we look at the services here, so we're going to describe the services, what you'll see is that there's a load balancer that is federated over lots of different IP addresses, and those IP addresses are the different IP addresses of the different clusters. And the end result, the big surprise here is that we get a white Nginx default page. But this is a super highly available default Nginx page. It's globally replicated. The DNS is highly available. It's super awesome. So if you wanted to put like a Nyan cat on here, like the entire world would see permanently. So that's the Federation API, and that's the Federation API in practice. Like I said, it's a work in progress. This is what Federation 1.4 is capable of doing. There's a lot to be done left in the future, but it is a great reflection point, and you can kind of compare and contrast it to self-hosted, where self-hosted is at the bottom, Kubernetes on Kubernetes, and cluster Federation is at the top, Kubernetes on Kubernetes. It's a pretty neat model, and really shows off the power of Kubernetes as a platform for not just handling our stateless web applications or our 12-factor apps, but of handling these complex deployments that a lot of us find ourselves managing. Yes?
Where does the Federation control plane itself live, and how does availability of that work?
Absolutely, great question. So how does high availability of federation work? Going back to these great diagrams, so what happens, I have deployed the Federation API in a single cluster. Obviously, that's not what you want. You want NetCD replicated over lots of things, but it's really hard to set up, so I didn't because I'm lazy. The way it should work is that you essentially run the Federation API server over all of your clusters, along with that replicated NetCD, and these are replicating essentially globally. And so these are put behind load balancers. Those load balancers end up in some sort of globally, it depends on how you want to set this up. If your cloud provider can handle it, or your ISP, or whoever, or maybe you just put DNS records with really low TTLs. But you put those load balancers inside of a DNS record, say in the naive case, and then if any one of those data centers goes down, you either trigger automatically through like global monitoring. You want to be really careful with that, but trigger automatically removal, or you manually remove, and you're able to talk to the surviving federation clusters. Make sense? Yes?
So earlier in this decade, Amazon had some high-profile outages, and when I looked into them carefully, whole regions went down because of failures propagating from one AZ to another within the region,
Yep.
through the region control plane.
Yep.
Why won't that happen here with problems propagating through the federation control plane?
Yeah, for sure. Like if you overload your clusters, like that's going to cause problems. The advantages that we have is that containers allow us to do better resource isolation, where ideally you're able to, through the kubelet and through the Kubernetes isolation of namespaces, we're able to actually ensure that we don't overschedule or over-provision. But assuredly, just like a for loop or parallel SSH, like you can definitely get yourself in a massive bind with these sorts of systems. It just comes down to monitoring and good
I wasn't really
practices.
overloading
Yeah.
the whole thing. I mean, it's obvious. If you overload the whole thing, you're overloading the whole thing. But the pieces where, for example, in one AZ, it gets kind of wedged.
Right.
And the problem is the control plane gets wedged because one of the AZs it was dealing with is kind of wedged.
I see. So the advantage that something like Federation has is that it's kind of like pushing down from the top and then recovering events back through. And so you absolutely can like end up in places where bugs and stuff will take out the whole system. But it is very much a like tree-based system where the root is pushing down. There's not really a lot of like RPC happening between the two systems actively to like do active health monitoring and that sort of stuff. So I'm definitely like dodging, but it is a fairly like well-designed abstraction. Yeah.
So the load balancing, does it just do round robin, or is there any way to have it more than that?
Yeah, so I'm super punting on load balancing by using the Google Cloud load balancers. So they're actually, the Federation API is like setting up all the DNS records under g.ifhub.org. And so it's setting up all the federated DNS records and then creating the load balancers and managing all that for me. The Federation API is doing that on my behalf, but I'm kind of like punting on that hard. Again, it will depend on like if you have globally replicated or like multicast or whatever way of like having a stable IP that is viewable globally for your web application or your DNS name. That's what you're going to have to integrate with.
But when it's forward, you can do like geolocation sort of.
Yeah, exactly. Yeah, you could start to do that sort of stuff where you have like a serve record and you're like pops actually figure out which one is the correct one. Yeah. Yep.
Your rolling deployments are happening in parallel in each cluster? Or is it like
Oh, yeah. So right now, only replica sets are supported. You can't really do like deployments. And so when you like update the replica set, it'll essentially like the Federation API and controller manager are pushing, like you need to be running these replica sets or these pods, pushing it down to the cluster.
So each cluster basically manages its part individually?
Yes.
And it maintains that site of that region is always up and running?
Correct. So the clusters are acting independently. Yeah. So the Federation API supports ingress services, namespaces, replica sets, secrets, and DNS, which, as I mentioned, is cloud provider specific today. So the next steps with Federation, There's to check out the Federation setup guides at kubernetes.io. They kind of give an overview of how the whole thing works. Kelsey's guides, like I mentioned, are easier than the official guides right now, so you may want to check those out. SIG Federation meets regularly. Quentin leads SIG Federation. He's in the back of the room there wearing a bright blue Kubernetes shirt, so talk to him if you're interested in this. And it's an interesting project and rapidly developing. So what do all these disparate things have in common? Why did I throw them all into one talk? One is that I didn't think ahead. Two is that there's actually like shared vision here. So with these operators operating etcd, we can have etcd going across and actually handling this complexity of how do I get etcd replicated across these different AZs. Self-hosted, you can imagine starting to manage Kubernetes itself, and Federation managing lots of Kubernetes clusters. So these abstractions are very similar. And one thing I just want to continue to point out is this is all leveraging tested designs. We trust Kubernetes, and the Federation APIs are very, very similar abstractions and very, very similar designs. So my goals from here, I want to make self-hosted the default for Kubernetes clusters, or perhaps at least the preferred deployment model. I want to make it easy to operate etcd for single and federated cases. That's why we've introduced the NetCD Operator work that we've done. I want to bring these Federation technologies to market because I think over the entire time that I've been involved in the cloud and infrastructure market over the last 8 or so years, all that I've ever heard about is hybrid cloud. And gosh darn it, we want to bring hybrid cloud actually to market. And I think this is probably the best way and the best shot that we have of doing that. If you want to learn more about this stuff or what we do at CoreOS, or you happen to be in New York in December, we have a conference December 12th and 13th, a bunch of companies getting together talking about how they're using Kubernetes, how this whole cloud native thing is working inside of their organizations. And with that, I would like to thank you for your attention, and I'll take a few more questions. We have about 3 minutes, and that is that. Thank you. Yeah, in the middle.
Can you help me understand the difference between a Helm chart and the operators?
For sure.
Can you help me understand the difference between a Helm chart and the operators that you discussed?
Yeah, so this is a question that operators, CoreOS. If you go read the blog, there's an FAQ at the bottom about that. The big thing is that Helm charts are about packaging up a set of essentially Kubernetes resources as like a single object, whereas an operator is actively managing a complex piece of software and doing on behalf of the user like a lot of the tasks that they would have been thinking about doing. So like we think of it as operators represent human operational knowledge, those things that you would have runbooks for, but in software. And because Kubernetes, we have a full cluster view of what's going on, we can do those runbooks automatically, like resizing clusters, backing up clusters, et cetera. And so we introduce operators for both Prometheus and etcd. And it's about this active management component, and then using and extending the Kubernetes API so that I can do things like kubectl, git, etcd controllers, and actually think about them as just normal resources, even though they weren't resources that Kubernetes naturally has.
So operators is not a new primitive of the Kubernetes API.
Right, so the question was, are operators a new primitive of the Kubernetes API? It's really a pattern that contains two things that Kubernetes has always been able to do. It's always been able to have external controllers, so these pieces of software that act on behalf or act on the Kubernetes API, running on the Kubernetes API, and the idea of a third-party object or third-party resource. And so combining these two things, this active management component and this idea of a third-party resource, is what makes an operator an operator. Yes? Yeah.
Is the Federation API server developing out of the existing API server, or is it something else, I mean, built from scratch?
Yeah.
The second question is the etcd cluster, operators or otherwise, should I treat them as something part of infra Kubernetes, or should I treat them as etcd as a service and use it for applications and Kubernetes together? What's the recommended way?
Yeah, so good questions. On Federation API, it is leveraging essentially all the same abstractions the API server has, but it's a subset and operates differently than a normal API. For example, like Git pods isn't a resource. So there's a lot of abstractions that are being leveraged. On etcd, So etcd is a very performance sensitive application. It is doing its best to essentially do, as by analogy, like RAID between lots of machines, only for this important configuration data. And so our recommendation is that you use a single etcd for Kubernetes, and things like operators make it easy for you to launch additional etcds for your individual applications. In a lot of cases, some of the really critical applications like your network systems like Flannel, Canal, Project Calico, Weave, et cetera, are moving to running on top of the Kubernetes APIs themselves instead of talking to etcd directly. But there are a lot of applications like Vault or Traffic or others that want or sometimes utilize etcd directly. So for those applications, it totally makes sense to manage your own, or at least deploy an etcd for those. Yeah. Sorry, you asked a question really early, so I can just repeat.
Yeah. So I wanted to ask if in the federated setup, it could be multi-cloud between different public clouds?
Yeah, exactly. So that's the entire goal. So the question was about multi-cloud. The entire goal is that you're able to, initially, it's probably easiest to be like, I'm going to run in multiple AWS regions. But you could imagine essentially being able to start to play the games where I run on Azure, I run on AWS, and I load balance between those. Maybe I don't trust one of the providers, or I'm going to start to play games where I notice pricing differences, and I run my jobs depending on where the pricing is good. So that's absolutely the goal and the plan. Yep, I'll take I'm a little over time, so I'll take one more question.
You mentioned you want for the federation to run the etcd across the globe, essentially.
Yeah.
How sensitive is etcd to the latencies there?
Yeah, so etcd operates on this idea of leader election. The way we do leader election is based on responses. And so you can tune etcd to be, say, as long as you respond within a second, it's OK. So etcd is performance sensitive, but it's performance sensitive to whatever window you tune it to.
But
so by
consensus too.
what?
It's consensus. Every update takes a consensus.
Absolutely, yeah. And so in that case, like, it's not going to be the world's fastest federation API, but it'll replicate the data correctly, right? And all you're thinking about is tuning that election timeout so that it is the correct latency that you expect over your transatlantic link or whatever. And this is exactly, if you read some of the material from the Google site reliability engineering books, they have this idea of cluster chubby. Chubby is like the equivalent of etcd inside of Google. They have the idea of cluster chubby and global chubby. And so what we're creating with the federation etcd is essentially the global chubby. Yeah, terrible naming. All right, I have more stickers up here. I'll take a few more questions and then hang out. But thank you so much for your attention.